Good afternoon. So after all the observation that Barbara showed us about the inner structure of the mantle, we're going to talk about the dynamics and the physical phenomenon that are producing all those signatures. So you saw all the structure that this dynamics of the mantle can produce, and it's due to convection. And we know that the main surface signature of this mantle convection is plate tectonics. So today I'm going to talk just a little bit of plume, but mostly of how can we produce plate tectonics just from convection. And in fact, it's not so easy, and you can produce subduction and plate tectonics because of the very particular properties of rocks, and especially of the lithosphere as it deforms. So deformation of rocky material depends very strongly on temperature. So we all know that on the surface we observe a lot of faults, and we get earthquakes. So we have a brittle material when it's cold, but then we know also that the mantle is moving, and this is because at the geological timescale, it's a viscous material, like honey. And then in between, the lithosphere, the plate, is also, as the temperature is decreasing, going from viscous to viscoelastoplastic to brittle. And it's this complex material that we have to break to produce plate tectonics. So before I continue, I just want to say thank you to a number of people. First of all, probably to Xavier Le Pichon, because I'm here today probably in part of the Opération Famous campaign in '73. I was about 10, and I was just fascinated by all the results that were coming from diving deep in the ocean with the discovery of the life on the mid-ocean ridges. And then, of course, I learned at that time also of plate tectonics, and I was thinking that it was pretty cool that such a big object as a planet was moving beneath our feet, and it would be really great to be able to understand a little bit about it. So that's how I did physics, and I'm here today. So, but of course I haven't done all this alone, and it's also part of the fun. And I want to thank all the great students, postdocs, colleagues, both in the physics, fluid mechanics realm, and also in all the geophysics, geology realm, who helped me to think about plate tectonics and mantle convection. So, as we saw this morning, in the solar system, right now the Earth is the only one that has plate tectonics. And this is really important to understand it, because as we to understand why, because as we go much further and discover new exoplanets and so on, and are looking for an Earth number 2, well, what is making first Earth number 1? So, but what is plate tectonics? So we know from, for example, the recording of seismicity over the year that the lithosphere, the surface of the Earth, is cut into plates, and that deformation is very localized on plate boundaries, either on the mid-ocean ridges, or on the subduction zone. And then we know also through the age, the map of the age of the oceanic lithosphere, that those plates are moving continuously. They're created at the mid-ocean ridges, and they plunge back in the mantle at the subduction zone, like, for example, under Japan. And this subduction, it's asymmetric, so it's one plate going underneath another one. And then, if you look at how the motion is distributed on the surface, there is all the divergence and conversion that I just talked about with accretion and subduction. But there is also a signature of vorticity, so slip between two plates and rotation on the surface. And this is very different from what you could observe in a simple viscous fluid, like, for example, water or even heavy oil. This is really a signature of the complex rheology of the lithosphere. But plate tectonics is also a very organized and continuous process. And as I was saying, it's the surface signature of mantle convection. So what we want to understand how plate tectonics is going on, we have to take into account all this. And then the big question is, when did it start? And on this figure, you can see that, so it's a review paper, and you've got all those black dates are the ones that have been proposed for the onset of plate tectonics. And so it's all the way from nearly the beginning of the solid Earth, more than 4 billion years ago, to 600 million years ago. And so why is it so dispersed? Well, first of all, it depends very heavily on the data that is available. And plate tectonics, yes, you're sinking back in the mantle, so you're destroying a lot of the record. So that's going to be a big issue. And then how do you define what is plate tectonics? I mean, if you use just subduction as a necessary condition and maybe a sufficient condition of plate tectonics, then you're going to see that it can start quite early. But if you look for the global organization and the full Wilson cycle with continental drift and so on, then it could take a much longer time. So this is also an issue. When did it start and how? So first of all, mantle convection. So as Barbara told us already, so the mantle, the solid mantle, 3,000 kilometers under our feet, is heated from below by the core. It's also internally heated, and it's cooling from above on top of the lithosphere. And we have a very large temperature difference between the two. So it means that if you isolate a parcel of this mantle, well, the hot part is going to be also less dense, and so it's going to rise, but the cold part is going to be denser, so it's going to descend in the mantle. And so this is the engine, the thermal buoyancy of mantle rocks due to temperature difference. But then we have two diffusive processes that want to oppose this. So first of all, since we're talking about heating, we have thermal diffusion. And this thermal diffusion wants to dissipate the temperature anomaly, so it wants to dissipate the motor of convection. And then we have also momentum diffusion. So the viscous stresses are resisting motion. So those processes are really the ones that are governing the first order of convection in a planet or in a star. And so the dynamics is characterized by two dimensionless numbers that just represent balance between those different elements. So the most important, I would say, is the Rayleigh number that compares the buoyancy force to the two resisting effects. And you can see that you're going to have convection only if the buoyancy force is sufficiently big to completely overcome those two resisting numbers. So there's going to be a critical Rayleigh number under which you will have no convection. And then there is the Prandtl number. And the Prandtl number, in fact, is comparing the two diffusive processes. So is thermal diffusion the one that is the quickest, or is it momentum diffusion? And so you can look at, you can determine in which type of regime of convection your system is going to be if you can calculate those two numbers. So those two numbers are based on the temperature difference in your system, on the size of your system, h, on the gravity, g, and on the physical properties of the systems like thermal expansion and those two diffusivities. So here I plot where the planet should be as a function of the Prandtl number and the Rayleigh number. Well, when the planet is starting, it's very hot. It's probably molten, so the magma ocean stage. And then you see that you are in the orange box. So it means that you are really at very, very high Rayleigh number, so the intensity of convection is extremely high, but you have also a low Prandtl number. What does it mean? It means that if that momentum is diffusing proportionally less than temperature. So as soon as you cut the engine of your motion, well, the motion is not going to stop right away. It's going to have some inertia, like in water, or in your teacup. If you turn your tea, if you just stop to turn your tea, the tea is continuing to turn. It's inertial effects. If you do this in honey, well, you stop your engine, you stop your spoon, you're going to stop the motion. There is no inertia. It's a high Prandtl number fluid. And that's exactly where the solid mantle are. So we're starting from a planet that is extremely hot, liquid, and so it's very turbulent. Rotation is important, and it's very hard to model, either numerically or in the lab, or it's impossible at those numbers. But when you go, when you go to a rocky, solid interior, then you can forget about inertia and the Prandtl number, and then you just have to worry about the intensity of convection. And this intensity of convection for a planet is typically between 10 to 6 and 10 to 9. And the good news is that both nowadays numerical stimulation and experimental and laboratory experiment can reach those type of convection intensity to study convection. And you don't have any rotation either. So, if first of all in this first approach, I just have, okay, I've got my Rayleigh number. It is going to determine the dynamics of my planet. This is if my planet has a constant viscosity throughout. We have some estimate, about 10 to 22 Pascal seconds. And then we see that the experiments, both numerical and lab, have shown that as a function of, as the Rayleigh number is increasing, you're going from cellular convection, like rolls or cells, and then you go, when the Rayleigh number is greater than 10 to 6, you go to plumes. And what the plume are doing is that, okay, for example, we are looking here at a similar situation at the hot core mantle boundary, and you've got the colder mantle above, and you see those white lines are temperature lines. And you see that as time goes on, A, B, C, D, first of all, you have a very constant and conductive layer that has most of your temperature difference, and that's what is called the thermal boundary layer. But then at some points, it becomes unstable, and you've got those nice mushroom-shaped plumes that Barbara was talking about. So this is what we would predict for the mantle. So it explains hotspot by mantle plumes very nicely. And if you add a bit of compositional heterogeneities into your mantle, well, you still have plumes, but you have a diversity of plumes and a diversity of shape. And that's, again, a good news, because that's what we observe in the mantle. But the big absentee is plates. I mean, in this thing, we should have hot plumes and cold plumes. We don't have surface plates. Surface plates, it's more like a cellular. It should be in the cellular regime. So how to make a plate? Well, we know that rock material have a viscosity, a rheology that depends very strongly on temperature. And the higher the temperature, the more fluid it is. So within the lithosphere, which is the top plate, the top cold thermal boundary layer, you can have a viscosity ratio of more than 10 order of magnitude. So that means that you're going to have a very strong asymmetry between your hot boundary layer that is very runny, and then your cold boundary layer that is going to be quite stiff. And actually, you can get this by doing experiments in honey, and you're going to observe, again, on the temperature profile, a very developed cold boundary layer and a much smaller hot boundary layer. So now, if I vary the viscosity ratio, so on top of my Rayleigh number now, to characterize my system, I need the viscosity ratio, that is the viscosity of the top stiff fluid over the viscosity of the hot runny one. And so for small viscosity ratio, you just have still plumes and a mobile surface for Rayleigh number of about 10 to 7, for example, typical mantle value. And just what it's doing is that the morphology of the plume is changing a little bit. Here, you see that the mushroom plume on B is the hot one, but that on D, the cold one, is more of a finger. Then if you are going to viscosity ratio greater than 10,000, then you're going to have a plate. I mean, the really viscous part of the thermal boundary layer is just too stiff to move. And so to save energy, you're going to have convection that is going to develop in a sublayer. So we have a plate, but this plate is never going to break. And so that's great, because that's the stagnant lead that you can get in Mars, in Mercury, probably on the moon at the beginning, and so on. But if we go to intermediate viscosity ratio, then it's quite interesting, because you can have several plumes now, but that are encased into a cold cell. So as you see here, I have like 3 to 5 plumes on the right, and you can see this big downwelling on the left. And this is just a cross-section, but if you move the laser light, you're going to indeed describe cold cell, but always hot plumes. And that's great, because it really begin to look a lot more like the Earth, with those LLSVPs, with a concentration of plumes that are surrounded by the cold downwellings that are the subductic plates. The other problem is that if I put the Earth into my diagram viscosity ratio as a function of Rayleigh number, it should be up there with Mars and the Moon and Mercury. So it shouldn't break. So why is it breaking? So in fact, breaking the plate, it's really a question of localizing the deformation. And if we just invoke convection in the mantle to do this, well, the convective stresses that we have are quite small, just 10 to 100 megapascal. So, of course, quite small compared to what? Well, if you look at the rock rheology on small samples, centimeter samples, then this is the type of rheology that you get. So at high temperature, it's flowing with either diffusion creep or dislocation creep, and at low temperature, it's just brittle. But you can, if you look at the differential stress on the top there, the strength of the lithosphere, and you can see that, in fact, there is a big zone in your oceanic lithosphere where the strength is more than at least 300 megapascal. So this is really a problem. How do you break this thing with just convection? But what I'm showing, I just showed you, was on small samples. And we know that we have subduction and convection on length scale of 100 to 1,000 kilometers. And when we look at the lithosphere, we know that there is a lot of heterogeneities, a whole continuum of scale with different processes. So on the micro side, so the grain size, diffusion, dislocation, so on. But at the meso-macro, you've got shear zone, dikes, faults, volcano, mountains, all those heterogeneities in the lithosphere. And so when we're looking at the strong localization of deformation and self-weakening that is needed to get plate breaking, the question is, is it really controlled by the grain scale, or is it controlled by this messy mesoscale lithosphere? So one way to deal with that, and especially numerically, is to assume an effective rheology, saying, okay, we know at high temperature it's flowing, and at low temperature we're going to reach a yield stress, and then at this yield stress it's going to flow. So it's like it's breaking. And when you implement this kind of law in a convection simulation, well, it's really great because you can get now the plates, and you can get plates that are subducting, accretion, hot plumes, and so on. So I thought that Nicolas Coltis will describe all this. So I'll be much briefer than he would be. So with this effective rheology, you can localize deformation, definitely. But this time, you have a fourth number. So I had Prandtl number, I don't count, but Rayleigh number, viscosity ratio, and then now you have the yield stress, the strength of your lithosphere, that you can compare, for example, to the the convective stresses, and depending on the value of those numbers, you can get in the stagnant lead. So your yield stress is anyway too big, and you cannot break the plate. You can get the mobile lead, so you can break it and get a continuous slab going down. But there is also a very interesting regime where you're episodic with, you are in the stagnant lead, and then suddenly you break it, and then you rebuild your stagnant lead, and you break it again, and so on. And that's what is called episodic lead. And Julia told us a little bit about it this morning. And if you, of course, we all know that beside temperature, the properties also depends on the depth of the mantle, the pressure a little bit, and you can add different ingredients. But the bottom line is that to get into, to have a chance to get in the mobile lead, your yield stress has to be at least less than 100 megapascal. And so you can also complicate it further, the system, and consider also melt intrusion. And then in this case, as Julia showed us this morning, if you plot the surface yield stress and the melt intrusion efficiency, then you can get, again, stagnant lead, episodic lead, mobile lead, but you get also this heat pipe and the plutonic squishy lead. So those two are not really going to break the lithosphere in the sense that I'm going to have a full-blown subduction going down. But it can extract heat quite efficiently from the planet. And in all this, anyway, you always find that the yield stress has to be less than, at least less than 100 megapascal, and even probably less than that. So but how can I determine the yield stress from the properties of the rock? What does it really represent? We don't really know, but I think it's not a coincidence that, in fact, this yield stress that allows the mobile lead, is happening, is of the same order as what the convective stresses are going to be produced by convection in your mantle. So it means that if the strength of your lithosphere, your yield stress is greater than the convective stress in your mantle, you're not going to have another thing than a stagnant or episodic lead. So how to break the plate? With those effective viscosity, the plate usually doesn't have any memory, so it cannot store damage. But we know that the lithosphere can store shear zone, faults, and so on, so damage on a very long time. It has a memory. So using this concept, Berkovici and Ricard make a breakthrough, and by considering two populations of grains, the dynamics of two populations of grains that were deforming under the diffusion creep. And so when you have damage because of the shear of convection, your grain size is diminishing, and then in diffusion creep, it means that the viscosity is diminishing. And then when you have, but you have also healing. When you stop the shear, the grain is going to grow again. But if you have two populations of grain, in fact, you can have Zener pinning, and so your grain size is increasing, but with a time scale. And this time scale can be quite long. So you're building a memory. And if the lithosphere stores damage a little bit everywhere for a long time, it weakens. It's going to weaken greatly. And so starting just from convection and a completely homogeneous lithosphere, it would take about 1 billion years to break it. On Venus, this breaking would never happen because healing is too fast because of the hot temperature. But then there are some hints that there might be subduction on Venus. So is there a way of going faster? So we've been trying to find some fluids in everyday life that had the same kind of rheological behavior as a rock. And so I told you a rock, I want it to be cold, brittle, hot, viscous, and in between, more complicated. And so we found those colloidal silica dispersions. Their rheology and density depend very strongly on the particle content. And so it's a nanoparticle of silica. dispersed in a liquid solvent, water and ions. And so if you are, instead of cooling from above, evaporating from above, you're going to build a plate, a stagnant lid, a skin, and the skin on the top is going to be more like brittle. And then if you go toward the mantle, viscoelastoplastic, and then viscous. So when we're looking, what is nice in the lab is that you can have access at all the different scales from the nanometers to the meter or decimeter where convection is going on. And so we see that if I put my top skin, my top plate, under the microscope, I can see shear bands, I can see fracture. We got also wrinkles and folding due to elasticity of the plates. And eventually, we do get one-sided convection, that is one-sided subduction, that is just arising from convection. And so, in this case, why is it subducting? So it's because of this complex rheology, but it's also because my skin, because of the evaporating flux, is in compression. And so as we know, when there is a compression, it's much easier for the plate to break and to get the subduction going. So here I had a plume going on the right, and I had also some mantle upwelling on the far left. And so in fact the plate that is in yellow here is in compression, and again you've got subduction and then subducting and spreading on the bottom of the experimental mantle. There is also another way, and if you have a plume and then it's rising up, when it's impinging under the skin, it's going to put it in extension, and so it's going to break on the top, first as rift, as fracture, and then as the plume is spreading at the surface, it's going to push down, it's going to initiate the subduction. And that's what you're seeing in this movie. So, but in this case, subduction is always by rollback. And in fact, it's never encompassing, it's never renewing the whole tank. And why is that? Well, the surface, it's a solid. So if it has to roll back, it means that on the edge of the subduction zone, or trench, I have to tear the lithosphere, and it costs energy. So in my case, every time the plume is finished to spread, then the subduction is just stopping. And so it's a very localized system. It's episodic, but randomly through the tank, and it's rolled back by subduction. You can run a lot of experiments and get some systematics that you can, and scaling laws as a function of the parameters of convection. And in this case, you can predict where any planet would be. So here, as a function of potential temperature and lithosphere thickness, you see if I'm really at the top, then no subduction because the plate is not buoyant enough. And then if it's on the red corner there, the lithosphere is just too strong because it's too cold, and so it's not going to break either. So you have a sweet spot, and you see that for the Venus curve, the Venus is a much more favorable case to have a plume-induced subduction than Earth right now. And I think that those plume-induced subduction could very well explain the very large coronae that we see on Venus, like, for example, Artemis. There isn't much plume-induced subduction that have been spotted on Earth right now. Maybe the Caribbean, maybe one or two other cases, but right now, definitely, Venus is a better candidate. However, in the Archean, when your mantle was much hotter, so it means that also your lithosphere was softer, so it was easier to bend, and once fracture was in, then you see that in the Archean, this plume-induced subduction was probably much more frequent. And that's also very interesting because, okay, it can produce subduction, but when we look at the craton formation, there's always this plume event in small quantity, and then most of the craton is granitoids that are attached to this plume event. And granitoids, that's subduction. So I would say that this plume-induced subduction is also a good way to form cratons. The same material, if you just put it under extension, you've got all the pattern of accretion that you can get on mid-ocean ridges, like transform fault, overlapping spreading centers, and also the microplates. So, how to break the plate? Well, subduction can occur spontaneously in our laboratory experiment if there's still if there's still between 0.1 and 2% of free liquid remaining in the experimental lithosphere. So, I'm not claiming, of course, that we have the Earth in the lab, but that suggests to me that melt could be very efficient at enabling subduction and then plate tectonics. In fact, probably that if you've got two phase and one much softer than the other one, it could work also. Weak layer interconnection is producing complex rheology exactly like the one that we have. But it's nice to see it in the dynamics in the lab. And then there is a lot of different ways of triggering subduction. So impact, gravitational overturn of the first crust, lateral compression, we talked a lot about it, and hot plume impinging under the lithosphere. You can see also that as far as lateral compression is going on, well, it means that it's much easier now with plate tectonics and plates moving around to initiate a new subduction zone by compression than if it started from scratch at the beginning. But one interesting thing is that with all those different mechanisms, it's probably quite easy for a rocky mantle to end its magma ocean stage with subduction. So I don't think that we go directly into a stagnant lead that is going to thicken and be very, very hard to break. I think that there is a good deal of mechanism that can help you to initiate subduction right away after the magma ocean. So we've got subduction. Is it sufficient for plate tectonics? And no. I would say that subduction is necessary, definitely, but it's not sufficient. In all the cases I showed you, usually it was mainly robot subduction. It was therefore episodic, a local system. You're beginning to have a plate that is moving. It's beginning to initiate subduction, and then it's really moving, but it's when there is another damage zone somewhere in the plate so that it can break at another point. So to get a plate moving, you got to have two damage zones. And to get organized plate tectonics as we see it now, you really need either a very long time to develop it, one subduction at a time at different places and so on, since it needs to store damage and increase the number of weak zones. And in fact, in the lab, we do observe both accretion and subduction only after a long time, especially, and never if we don't have any plumes. But then, if we have a synchronous event that can create a lot of damage zone on the whole planet at the same time, then you could organize plate tectonics much quicker. And this could happen, for example, if you have initially a mantle that is stratified with a slightly denser layer at the bottom of the mantle. So as the mantle is evolving through time, this bottom layer is going to increase its temperature until this temperature anomaly is going to go over the chemical density, and then you're going to have, again, instabilities, like the orange plumes that you see there. And when this happens, when the whole layer, such a whole layer on the mantle is getting unstable, the first time it's getting unstable nearly simultaneously. So it means that with this kind of mechanism, scaling laws show that you can have 25 big plumes hitting the top lithosphere at nearly the same time. And so that could be a good way to speed up organized plate tectonics. And so as I was telling you, we can get in the lab also very continuous subduction. And this time, so here you see a plate that is coming towards you. You can see also that there is some inner convection below the plates. There is several scales of convection in the mantle, and that's because of the complexity of the rheology. And, but this we observe in the lab only with plumes. So as a conclusion, I think that the necessary condition for plate tectonics, well, it's first of all to create plates, complex rheology, but also plumes. So to make a plate is fairly easy, just a strongly temperature-dependent viscosity. To break the plate, then it's much harder, but I think that a two-phase mixture, either two solid, but much better solid and liquid, so melt, can be very, very efficient to break a plate. So such a mixture of two-phase fluid liquid, solid liquid mixture, they're usually well described by a rheology with the yield stress, and that's good news because that's also the rheology that works very well in the numerical calculation. So subduction could have existed, I think, directly after the magma ocean stage, but that doesn't mean that we had organized plate tectonics right away. And plumes, I think, are probably another key for the development of plate tectonics and its sustainability. So we need, indeed, a very dynamic planet. And so I think that from the modeling point of view, both theory, numerical, and experimental work still has a lot of things to study because of those complex rheology. Thank you.